A solenoid consists of an insulated long wire closely wound in the form of a helix, so that the length of the solenoid is much larger compared to the diameter of the solenoid. Now suppose if current is allowed to flow through the solenoid in this manner. Let's say current enters from this point, it goes round like this, and it leaves from this point. So we know that whenever current flows through a wire, there will be magnetic field all along the wire. But because the solenoid is arranged in this manner, because it has this shape, the magnetic field will be of this form. So you can clearly see here that the magnetic field lines inside the solenoid are actually parallel to the axis of the solenoid. Not only that they are parallel, they are also uniform. Okay, the magnetic field inside is strong. How do we know the magnetic field is strong? Because if you look at the distance between the magnetic field lines, it's very close. In other words, the magnetic field lines are very close. That means they are compact with each other. So we can say here that the magnetic field is very strong compared to the field outside. Okay, if you look outside, the magnetic field lines are far apart from one another, indicating that the field outside is very small and it can be taken to be zero. But the field inside is uniform and strong, and it is parallel to the axis of the solenoid. So if the current is entering from here, the field lines are entering from this side of the solenoid and they are leaving from the other side of the solenoid. A few important points, first of all, that we need to remember, that we need to note. So point number one is that the magnetic field inside the solenoid is strong and parallel to the axis of the solenoid. Okay, so that is the first point. Point number two is the field outside. The field outside is very weak. And can be taken to be zero. Okay, so these are the 2 points that I want you to remember before we go into the derivation of the field inside of the solenoid. Let's say we have a solenoid which is cut along its length from the center. Okay, so a solenoid is actually like a cylinder, yes or no? So what we do is, let's say this is the solenoid. Let's say the cylinder is like that, and we cut along this line. We cut it in that direction. So if you cut in that direction, you will get this picture which shows the cross section of the solenoid. Right? So these small circles are actually the cross-section of the wires that make up the solenoid. So this wire here, I have drawn like this. I have drawn a circle with a dot in front, meaning that this wire is coming outward. Okay, so this wire is coming outward, and then here I have drawn a cross, which means that the wire is going inward. Got it? So from here the wire is coming out, going in. Then from the back, again from this point it comes out, goes in. Then it goes from the back. From this point it comes out, goes in. So you get the picture that the wire is going like that, round and round. Alright, so this doesn't look like a solenoid, but this is only the section of the solenoid which you have cut laterally along the axis of the solenoid. Okay, so let's say the current is flowing in that direction. Okay, in that direction. So this current is coming out from here. It is coming out from here and it's going in. Current is going out, going in, coming out, going in, like that. So if the direction of the current is in that manner, then the magnetic field produced inside of the solenoid will be in that direction. And remember that the magnetic field is parallel to the axis of the solenoid. Got it? Now, in order to find the magnetic field inside of the solenoid using Ampere's rule, using Ampere's law, we need to choose a closed loop. Yes? And like I discussed in Ampere's law, the closed loop can be of any shape. It need not be a circular shape all the time. So in this case, let us choose the closed loop to be rectangular in shape. Okay, let's say a closed loop P, Q, R, S of length L, let's say. That means the length from here till here is L. Right? All right. So by Ampere's law, what will be the magnetic field? What will be the magnetic field crossing only this loop? That is what we are going to find, right? So by Ampere's law, you have the integration of B dot dl. This is equal to mu naught into what? Into current passing through the loop. In this case, the loop is what? The loop is the rectangle PQRS. Okay, that is the loop in this case. We are not considering the current which is passing through the entire length of the solenoid. Only the current which is passing through the loop. That means only this part. Okay. So here you have mu naught. Current passing through the loop will be what? Will be the number of turns per unit length, small n, into the length of the loop, into the current I. Okay, let's call this sum equation 1. So before we start this, let us write something here. Let n be the number of turns per unit length. Okay, B be the magnetic field, and I the current through the solenoid. All right. Now what we can do here is this left hand side, we can divide it into 4 sections, to 4 parts. Okay. Now we can do like this. We can take integration from P to Q, of B dot dl, plus integration from Q to R, B dot dl, plus integration from R to S, B dot dl, and finally integration from S to P, B dot dl. This is equal to mu naught n L I. Okay, right. Now let us apply the dot product. We know that A dot B is AB cos theta, right? Here the L is a small length in the in this arm PQ. That means we take a small length, let's say a small length here. Okay, this is dl, right? QR, the length dl, we can take it to be this length. That is the length dl. Okay, in R, from R in the arm RS, this may be the length dl, and in the arm SP, this is the length dl, right? So we have to look at the angle that dl makes with the magnetic field. Okay, so the first integration will be from where? From P to Q? Yes, from P to Q. from P to Q, this will be B dl cos 0 degree. Why cos 0 degree? Because in this length PQ, dl is parallel to the magnetic field. So the angle between dl and B is 0 degree. So that's why we take cos 0 degree. Now in the length QR, from Q to R, this will be B dl cos 90 degree. I think you understand why this is 90 degree. If you look here, this dl is perpendicular to the magnetic field, so 90 degree. Plus from R to S, B dl cos, now let's do one thing. Let us take this to be 0. Do you understand why this is 0? This part will be 0. The third integration will be 0. Because if you look at the diagram here, Rs is outside of the solenoid. And what did we say outside of the solenoid? We said that outside of the solenoid, the field is very weak and it can be taken to be 0, right? So therefore, the field outside will be 0. So this third integration will be 0. And finally, from S to P, this is B dl cos 90 degree, and that is equal to mu naught n L I. Okay, and do you agree or not that will be 0? This also will be 0 since cos 90 is 0. So we are left with the first integration from P to Q, and this becomes B dl. Okay, that is mu naught n L into I. B, I can take it out of the integration sign. So basically we are integrating from point P to point Q. If you integrate from point P to point Q, you are getting the entire length L, right? So this integration will be L, mu naught n I L. Okay, so this L and this L will cancel. So therefore, the magnetic field is equal to mu naught Ni. Right? This is the required expression of the magnetic field inside of a solenoid. Let's say this solenoid has a core. Since that, let's say there is a, sorry about that. Let's say there is a core like this, okay, and this core has got permeability mu r. Then in that case, what will be the expression of the this magnetic field? Okay, let us write that down. If the solenoid has a core having permeability mu r, then this expression B will simply become mu r mu naught n I. Okay, let's put this inside of a box. Another point that is important to consider here is at the ends of the solenoid, the magnetic field is half of this. Okay, so you have B is equal to half mu r mu naught n I. So this is only the value of the magnetic field which is at the ends. That means at this point, and that point of the solenoid.